Section 25.2 Molecular term symbols. Molecular term symbols are similar to atomic term symbols. You will first determine the quantum numbers for individual electrons, and then you sum up their Z components. From the sum of the Z components, you determine the total angular momentum quantum number and the total electron spin quantum number. Now let's look at some simpler cases, such as diatomic molecules. In a diatomic molecule, the molecular axis is often chosen to be the Z-axis. The Z components of the angular momentum and electron spin of the diatomic molecule are denoted by m sub L and m sub S. All those are uppercases. We use lowercase l, s, m sub L, and m sub S for electrons in the atomic orbitals, single electrons in atomic orbitals. But this L, S, m sub L, m sub S in uppercases, they are sum of the vectors. For electron in a sigma molecular orbital, m sub L is 0. Well, this is because m sub L is 0 for s orbitals. So when you form a sigma bonding orbital from those s orbitals, well, m sub L is still 0. For an electron in a pi orbital, m sub L is plus 1 or minus 1. Well, this is because m sub L is equal to plus minus 1 for px or py atomic orbital. And a pi orbital is simply the linear combination of px or py orbitals. Well, to be more precise here, we need to use p minus 1 and p plus 1. P minus 1 and p plus 1 are the linear combinations of px and py. For example, px plus I times py and px minus I times py. But in this case, for simplicity, we'll just use px and py and say they have the z component of the angular momentum has a quantum number of m sub L is equal to plus minus 1. Well, what if we have a sigma bonding orbital formed by the constructed interference of two pz orbitals? Well, m sub L is 0. Why? Because pz is equivalent to p0, and p0 has m sub L being equal to 0. Now let's look at this hydrogen 2 molecule with 2 electrons occupying the 1 sigma g orbital. First, it's a sigma orbital, so m sub L is just 0 for both of the 2 electrons. The sum is going to be 0. Now let's look at the spin. You have 1 alpha and 1 beta spin. Therefore, the sum of the z component of the electron spin of the 2 electrons is also 0. Note that this m sub L can have multiple possible values from negative L to positive L. So negative L and positive L serve as the lower limit and upper limit of m sub L. But now m sub L can only be 0, therefore the range is from negative 0 to positive 0, therefore L is 0. Same here, m sub S is from negative 0 to positive 0, therefore this uppercase S has to be 0. How do we write the molecular term symbol? Well, it's just we use 2s plus 1 in the superscript and the notation for the angular momentum here. So remember, in atomic term symbols, the notation is 2s plus 1 and then L. For molecular term symbols, we run out of English letters, so we use the corresponding Greek letter, lambda. Lambda corresponds to L. So in this case, this is uppercase lambda. That corresponds to uppercase L. Again, we use the same rule for the symbol to be used. Well, L is 0, 1, 2, 3. In atomic term symbols, we write S, P, D, F. In molecular term symbols, we use Greek letters. Okay, we use sigma, pi, So SPDF, sigma, pi, delta, and phi. Okay, sigma, pi, delta, and phi correspond to the English letters SPDF. So in this case, L is 0, so we use sigma here. And the superscript is 2s plus 1. We know S is 0, so it's 1 sigma. This is the molecular term symbol for this hydrogen molecule with both electrons that occupy the sigma G bonding orbital. Because both electrons have the G symmetry, so you can look at this sigma G orbital. So you have both electrons with the G symmetry. And G times G is G. Therefore, the molecular term symbol for the ground state of H2 is 1 sigma G. By the way, G times U is U. U times G is U. U times U is G. G and U are referring to anti-symmetric and anti-symmetric with respect to the inversion center. What if we excite an electron from the 1 sigma G orbital to the 1 sigma U star orbital? So you still have 2 electrons, but they occupy 2 different orbitals. This is 1 sigma G. This is formed from the constructed interference between the 2 1s orbitals. This is formed via the destructive interference between the 2 1s orbitals. In this case, we can have 4 possible microstates. That means we have 4 different arrangements of this 2 electrons. How do we do this? Well, very simple. Now you have 1 electron in the 1 sigma G orbital. This electron can be alpha or beta. And then you have the electron in the 1 sigma U star orbital. And also there are 2 possible options, alpha or beta. So essentially you have 1 sigma G alpha, 1 sigma U star alpha, 1 sigma G beta, 1 sigma U star beta, 1 sigma G alpha, and 1 sigma U star beta, and 1 sigma G beta, 1 sigma U star alpha. So 4 possible microstates. And we can write out the wave functions for these 4 different microstates. So it's a little tricky because we need to ensure the total wave function of these 2 electrons is anti-symmetric. So we wrote out these 4 total wave functions. They are all in the form of a product of a spatial function and a spin function. A spatial function, spin function. Spatial function, spin function. Spatial function, spin function. So let's look at this S1 electronic state. This means the first excited state. This one means first excited state. And S means singlet. So this one triplet, first excited state. Now let's look at this one. The spatial function is symmetric. The spin function is anti-symmetric under the exchange of the 2 electrons. Now let's look at the 3 degenerate T1 wave functions. Well, in these 3 wave functions, the spatial function is the same. Look at this spatial function. It's anti-symmetric. Now look at the spin functions. They are different. You can have alpha 1, alpha 2. It's symmetric. Beta 1, beta 2. It's symmetric. Alpha 1, beta 2 plus alpha 2, beta 1. It's also symmetric. It's possible to apply the angular momentum operator and the spin operator to these wave functions to obtain the eigenvalues and corresponding quantum numbers. So I'm not going to do the derivation. I'm going to just give you those quantum numbers. In this 4 cases, M sub L is 0, 0, 0, 0. Why is that? Well, sigma orbitals always have M sub L equal to 0. So no matter how you kind of just do these combinations, whatever microstates you have, M sub L for individual electrons are always 0. Therefore, the sum is always 0. So this M sub L is the sum of the lowercase M sub L for individual electrons. But the lowercase M sub L for individual electrons are always 0. Therefore, the sum is always 0. M sub S, we'll have to sum up the spin. 2 alpha, the spin is positive 1. So plus half, we have 1. Minus half, we have negative 1. This is a little complicated, but if you apply the C component of the spin operator to this wave function, you'll get 0. So that's why it's 0. And this guy is also 0. Well, this is because qualitatively, if you think about alpha electrons and beta electrons, You can imagine this two wave functions are kind of just a mix of two different spins, and overall the spin cancel. That's why you have m sub s equals 0 here and also 0 here. The first three rows, they result in a triplet, 3 sigma u. This is called molecular term symbol with a degeneracy of 3. So again, this superscript is 2s plus 1. When you have a range of m sub s from -1, 0 to 1, that means s has to be 1. When s is equal to 1, 2s plus 1 is 3 over here. Sigma, that's the symbol that corresponds to L. And then you can see all zeros here. When m sub L can only be 0, the L has to be 0. When L is 0, we put a sigma symbol here. Again, when L is 0, 1, 2, 3, the symbol is sigma, pi, delta, and phi. So this has a degeneracy of 3. The last row over here, this row is a singlet. It's 1 sigma u as well with a degeneracy of 1. So why do you see a u here and a u here? Well, it's 1 sigma g and 1 sigma u. So really you need to multiply this g with u. G times u is u. We can also add another superscripts to the molecular term symbols, plus or minus. They depend on whether the molecular wave function changes sign or remain unchanged in a reflection through any plane that contains the molecular axis. So to do this, it's better to visualize those wave functions and picture the reflection with respect to a symmetry plane that contains the molecular axis. But there's a shortcut as well. So you can just look at these three rules. If all molecular orbitals are filled, plus sign applies. If all partially filled MOs have sigma symmetry, plus sign applies. Well, I think this is because sigma orbitals are always symmetric with respect to the symmetry plane that contains the molecular axis. Well, if you have partially filled MOs with pi symmetry, that's a little complicated. So pi orbitals are anti-symmetric with respect to a symmetry plane that contains the molecular axis. So that's why it's a little complicated. When we are looking at cases like O2 and boron 2, if sigma arises, if you're talking about sigma molecular terms, the triplet is always minus. The singlet is always plus. So for example, the ground state of O2, we learned it's going to be 3 sigma g and sigma arises, and it's a triplet, so it's minus 3 sigma g minus. This is the complete molecular term symbol of the O2 molecule. So really, how do we get this plus minus? You have to look at the wave function of this molecular term, and then you need to look at the symmetry of the electrons and determine if it's plus or minus, symmetric or anti-symmetric with respect to a reflection regarding a symmetry plane that contains the molecular axis. So for just convenience, you use the three rules to determine whether it's plus or minus. Alright, so since we were talking about O2, I want to write out the 6 possible microstates of the O2 molecule when we place 2 electrons in the 2 degenerate 1 pi g star orbitals. So there are 2 degenerate 1 pi g star orbitals because you can have px destructive interference, you can have py destructive interference. Right? So more accurately, we should not be talking about px, py, we should be talking about p plus 1 interaction and p minus 1 interaction. But just for you to be able to imagine the shape of the orbitals, let's say px, py, because p plus 1 and p minus 1 are complex functions. It's much more difficult to imagine complex functions. So now let's look at those quantum numbers for individual electrons. Those are angular momentum. You can have 1, 1, minus 1, minus 1, 1, minus 1, minus 1, 1. So what does that mean? Well, just imagine you can put both electrons in the pi orbital that consists of 2p plus 1 orbitals, 2p minus 1 orbitals, 1p plus 1 and 1p minus 1, 1p minus 1, 1p plus 1. So that's possible. Alright, so in this case, you put 2 electrons in the same orbital. Therefore, it has to be 1 alpha and 1 beta. In this case, you also put 2 electrons in the same orbital. So you have to have 1 alpha and 1 beta. In these 2 cases, you are putting the 2 electrons into different pi g star orbitals. So it can be alpha, alpha, alpha beta, beta alpha, and beta beta. We do a linear combination of these 4 microstates. We can get 2 different series of m sub s. The first series is from -1 to 0 to 1. The second series contains only one number, but still consider this as a range from -0 to +0, and therefore s is 0. Over here, it's from -s to +s, so s is 1. Same here. This is a range. It's from -0 to +0, therefore s is 0. So now we have the values for m sub l right here. It's the sum of the individual electrons. We have the sum for the spin of individual electrons. Now we just write out the molecular term symbols. So over here, this is a range from -2 to +2. But for molecules, it's kind of interesting. For writing out the molecular term symbols for O2 and boron 2, the range is this. The range is just minus L or plus L, nothing in between. So if you see m sub L can be -2 or +2, L is 2. That's it. It's impossible for this m sub L to be -1, 0, or 1. So this is different from atomic term symbols. In atomic term symbols, you need to have m sub L to be -2, -1, 0, 1, and 2 to determine that the value of L is 2. In the molecular term symbols, m sub L can only be plus minus L and nothing in between. So in this case, it's minus plus 2. Therefore, L is 2. So in this case, these 2 rows give you L equals 2 and S is 0. Now in this case, L is 0, but S can be 1 or 0. So we have 3 molecular term symbols. In these 2 rows, you have L equals 2. L equals 2. S is 0. L is 0. S is 1. L is 0. S is 0. So the first 2 rows correspond to 1 delta. So why? When L is 2, the symbol is delta. Again, when L is 0, 1, 2, 3, the symbol is sigma, pi, delta, and phi. So when L is 2, this is delta. 2s plus 1. So you have s equals 0, 2s plus 1 is 1. It's a singlet. It's a singular delta. The last 2 rows correspond to 3 sigma g minus. So these 2 rows, actually you can say these 4 rows, they correspond to 3 sigma g minus and 1 sigma g plus. So again, when when you are looking at a partially filled MOs of pi symmetry, such as O2 and boron 2, when sigma rises, triplet is minus, triplet is minus, triplet is minus, singlet is plus. So this 3 sigma g has a larger electron spin, therefore it has lower energy. So in molecular term symbols, you also look at the electron spin. When you have a larger electron spin, it has a lower energy. So that's why this 3 sigma g minus is the lowest energy electronic state for O2. All right. It should be followed by 1 delta and then 1 sigma g plus. Similarly, when you look at the ground state electronic term of B2, 1 pi u, it's also 3 sigma G minus. In this case, U times U is also G. I'd like you to watch this video to better understand the molecular terms for B2 and O2, so this video. And if you're interested, you can read this paper to see the detail. This is a paper published in the Journal of Chemical Education.